Hello everyone, my name is Roman Storchak and I am a Chief Data Officer in Fozzy Group. Today I will give a talk about computational data governance at scale. After my PhD in life sciences in 2009, I have switched to hands-on data science and technical management. Last 5 years, I am working as Chief Technical and Chief Data Officer in various industries. And my main interests are culture of data-driven decisions, all flavors of data ops and data infrastructure, and building high-performing teams. So in Fozzy Group, we have gotten one big goal, which was to decrease time to market for analytics by the factor of 10. We decided to tackle it with 3 separate but interconnected streams. The first one is we launched a Spark-based data platform with a lakehouse architecture. The second one was data and analytics governance stream, which consists of launching data catalog and data discovery, building data lineage and compliance, covering data and analytics governance with metric and appropriate business processes. And the third one is building Center of Excellence for Analytical Engineering and Center of Excellence for Data Governance. So our data governance is built upon a few basic but very important principles. The first one is that data can be trusted. The second one is that shipment of data goes according to service level objectives. Data or data products should be well documented and can be searched. Metrics and entities that are used by different teams and businesses should be standardized. Data should follow legally required policies. And data products are stored securely and can be accessed only by authorized users. Every principle except the last one is based on another one, which says that we have to achieve a very clear and straightforward ownership for data and data products and clear ownership over data pipelines. So let's find data owners. And we're dealing with relatively big infrastructure with more than 1 million tables in RDBMS. Most assets were created as a part of projects which teams were dissolved, which led to more than 60,000 stored procedures without full documentation and not all SQL code in the version control systems, not mentioning more conventional approaches, which are simpler to handle. So how come we landed with 160,000 tables in SQL Server in production? Fozzy Group, at least pre-war, is a pretty big company. We had more than 50,000 employees who are working in 30 different businesses, from retail, e-commerce, banking, insurance, manufacturing, delivery, tourism domains. Company is pretty old, so it leverages lots of legacy solutions that are good enough. And because the way it was built decades ago, there are lots of data silos. For example, every separate team might ask for a separate database server for them to serve their needs. So we started to build our inventory, and we're building it in a form of a property graph. We assume that each asset is a part of property graph with some entity types like datasets, tables, ELT procedures, dashboards, and charts, ML models. And each entity type has, and each entity has a set of properties, for example, ownership, relations, tags, etc. So to find all the entities and to find their metadata schema, we launched our data catalog initiative. We picked Data Hub to be our solution, which is an excellent product. It's open source, it has an active community, decent GraphQL and REST API coverage, which is improving. At the time of decision, it had to be on-premise, and it works well on-premise. It has both push and pull metadata ingestion, which we will talk about it later. Lots of connectors and well integrated with Apache Airflow that we're using. So when we started to ingest more and more metadata, we have found a few interesting bottlenecks. First of all, when you ingest hundreds or thousands databases, you start to realize that this is a long centralized setup process. Lots of databases to handle for a small team. Then we have found out that we're generating duplicates when we miss database aliases or mishandling case-insensitive names. We often asked ourselves question about completeness of access, meaning, did we get all the access to the schemas and tables or something is missing? And then another bottleneck, which at the beginning was very clear, but we anticipated that it would be less painful to developers, is that we have got stalling updates for schema changes and new table creation. So a developer or a team has to add human-generated metadata on the next day after creating the table, which is not so convenient. And pool-based ingestion often pulls technical and system tables, which has to be cleared later. So we had to build a framework, over ingestion framework, which helped us managing hundreds and thousands of databases. So basically, we collect all the databases, all the requests for data source ingestions. We check access rights automatically. We get full list of entities. We generate access requests if needed. Then we offload all the lists for tables, schemas, procedures, synonyms, etc., what is needed for analytics. And we enrich it with information about if it's a production or development or testing databases or schemas, etc., which is obviously stored in Git repositories and automatically ingested by Airflow DAGs, which are doing ingestion into Data Hub. So some of the takeaways that we have realized that pool metadata ingestion is a simple start. It has some drawbacks, and it requires automatization if you are dealing with many databases. And this automatization is company specific. So it's unlikely that it can be covered with some straightforward standard approach. So after ingesting a few hundreds thousand of tables, we started to look for owners. And owners absence of clear ownership is a bottleneck for any other data and analytics governance initiatives. So we started with a conventional approach, which consists out of two main roles: data owners and data stewards. Data owners are managers who are responsible for P&Ls, managing priorities, sponsoring and authorizing initiatives related to data governance. And data stewards are more hands-on roles who are often describing data, dealing with requirements for data quality tests, etc., and preparing functional requirements for data projects, which worked for decades before. But in our case, this approach generated owners for roughly 900 data assets in 6 months, which is less than 0.5% of what is needed. So we stopped and reiterated. We have redefined the ownership logic with a data mesh flavor, but it doesn't seem to be a data mesh. In our case, this approach works remarkably well. There are three types of owners who, namely domain owner, who are high-level managers who take part in global budgeting initiatives and can prioritize on the level of product portfolio. Data owners are often product managers or data managers who can efficiently manage a particular set of data products and prioritize the development of features of their data sets, dashboards, ML models, etc. And technical owners are those DBAs or developers who created or currently support these assets. And that is one of the key features of the ownership structure that we're leveraging. In our case, not all products have established data owner, or some products or projects reach their end of life or dissolved before. So instead of deprecating their data products, which takes way more time and efforts, we are reassigning we are using domain data owners in communication if data owners are not available. So we always have someone who is responsible. So we managed to redefine concepts and processes to gain leverage. And that led to some surprises. So from one perspective, business domain owners got more responsibility, that they managed to push down parts of their responsibility to data owners. But another one is we scraped multiple databases from service desk and other services inside the company to establish those developers who are responsible for managing data access policies. And we use them as interim technical owners if no other technical owner was found, which led to some interesting confusions. For example, veteran architects who used to be engineers have gotten roughly 12,000 tables to own. In our case, technical ownership was tracked on the level of databases. Hence, we propagated database ownership to the table level. So we had to build processes around it to offload some of the technical ownership from those champions. But we launched another interesting process, which helped us achieve our goal roughly 50 times faster than with the first approach. We used leverage. We found a small set of technical owners who helped a small data governance team identify domain owners, who later offloaded parts of their responsibilities to data owners. So we basically created a system which covers bigger and bigger amount of data sets later when it unfolds. As a consequence, we had to introduce one of the data and analytics governance performance metrics, which is % of data sets managed by domain owner directly, which is the lower, the better it is, because domain owners have to offload their responsibility to data owners. So we used implicit knowledge, which is hidden somewhere in internals of business processes inside the company as leverage, and it allows us to speed the process of assigning ownership by the factor of at least 50. Then we started to build relationship between assets, and unfortunately, it's not as a pleasant story as it might be. Relationships, especially for the old and outdated code, is pretty hard to build and manage, especially if you have very different data stack. We have a few classical technologies which company uses for decades, which is SQL Server, Bespoke Server, SQL Server Integration Services, and Oracle, and lots of newcomers starting from Amazon Redshift, Delta Lake, PostgreSQL, Elasticsearch, MongoDB, and many others. Another part of the story that company is heavily using table transactional replications to escape data silos. So we started from the obvious one to check how many transactional replications are in use. And we were surprised to find around 40,000 of them. And there is a champion table, actually the few, which has 75 replicas per table. So that is a simple part of the Lineage. We ingested table transactional replicas into the data hub and explicitly mark all the replicas. Also, we blocked changes to all the replicas, and we're propagating metadata from source to destinations. Also, another question was who actually owns the replicas. And in theory, teams that are consuming replicas are owning them, and only team that creates source table owns the source. But in practice, we did one-time ownership propagation over replications to enforce accountability, which stimulated data producers to catalog their consumers and offload their responsibility to multiple consumer teams. So, and then archaeological research on more data lineage. Most commercial lineage tools work well with toy examples, and they work well in small infrastructures. But in our case, we again had to build a tool over a data lineage tool in order to support our scale. First of all, we cache all the DLLs, we pre-process them, remove comments, we substitute SQL synonyms and do some other magic pre-processing, which helps us on the later stages. And after getting the lineage, we add host information with which our tools do not support, and we remove nodes that are not loaded to the data catalog because of the way Data Hub is managed and works. So when your lineage graph grows, the more issues with tracking lineage changes arises. Fortunately, it allows to soft delete objects and their corresponding relationship that were not ingested but were present before, but still it doesn't cover all the use cases. So we started to promote tools that collect metadata and lineage at runtime, which is dbt and airflow. And this is known concept as shifting data governance to the left. So data developers are getting increasingly more responsibilities to push lineage and to push metadata into data catalog directly, which strips all the needs for data stewards in older versions of data governance. So with Airflow, it's pretty straightforward. We're using custom lineage backend, but it requires a simplistic declarative approach where a developer inside the code has to explicitly show what are the sources and what are the destinations for Lineage. For DBT, the story is more interesting. It pushes schema and table column descriptions, easy to set up data ops, easy to learn, but it's the table level Lineage can be bypassed. So we introduced another metric, which is coverage with data lineage. And adoption of data lineage is extremely difficult, especially if it requires overcoming technical overheads or dealing with hundreds of thousands of outdated code. It is more manageable when teams are able to use technologies which treat Lineage as a first-class citizen, for example, DBT. But that is not enough in our practice. So we covered Lineage emitters with integration tests during CI/CD. For example, we used pre-commit hooks to trigger tests for completeness of metadata, descriptions, and completeness of data lineage for DBT, and pre-commit hooks for Airflow DAGs that check if tables mentioned in Lineage are correct. Without these small additions to data ops, coverage with data lineage doesn't really improve well. Then we started to tracking state of our data assets. And in our case, we have hundreds of human readable tags and a small set of machine readable tags, which are used in different logic, alerting, and analytics. And in our case, we started with one simple question: what data or data products does your team consumes? And basically, if a team consumes an external table, which means it automatically means that it is data product, irrespectively of the fact if it is treated like data product or not. So we created very simplistic but extremely useful set of consumption tags, which is ready to be consumed, not ready to be used, or not to consumed, or that this table is or this asset is consumed. Either way, it's marked ready to be consumed or not. And obviously, those tags can be human added or automate or added with different algorithms. So we explicitly add a bot ending to the tags, which are generated automatically. And why it is important? We are stimulating changing in corporate culture with technology. Successful data governance is about peer-to-peer communication, but in big companies, peer-to-peer communication doesn't happen by miracle. So our data and analytics governance initiatives build the core that stimulates direct communication between data producers and data consumers. Hence, we have to measure how different alerting and communication strategies influences data and analytics governance. So we asked a few useful questions. For example, how do alerts improve engagement rates for data catalog use? Do people tire? And when you work in a big company, this starts to reassemble more and more B2C products. If users have seen alerts, did it lead to improving metadata or not? Can we motivate stakeholders to improve data quality with alerts? What should be written in the alert, etc.? So we have found two major types of alerting and communication use cases. The first one are transactional alerts, and second one are metrics-based alerts. The first one are pretty straightforward. you just consume data that is not covered by data quality tests. We hope you know what you're doing. Or, hey, downstream alerts on schema changes or data quality test failed. Oh, sorry. If data quality test fails, we notify all the consumers downstream that something is wrong and they have to brace themselves. And another one, metrics-based alert, which are extremely interesting. For example, with metrics learning alerts, we stimulate meaningful interactions between data domain owners and data owners, or data consumers and data producers. For example, we routinely notify about changes of major data and analytics governance metrics. For example, that some data owners from your domain lifting off ownership somewhere else and where to, or that the data quality tests coverage increases, etc. In order to build metrics-based alert, we approached it as a straightforward analytical infrastructure. We collected events from Google Analytics, Amplitude, and directly parsed data hub database, moved it to data warehouse, and built a set of data marts. But in this case, treating data and analytics governance as a product implies setting a product hypothesis, experimenting, collecting data to support hypothesis, and measuring success. For transactional alerting story, there is a different technical solution. We required to measure performance, of course, but it had to be managed by non-engineers. Hopefully, Data Hub has metadata audit events that can be read from Kafka. So that was an easy part. And we selected to use UI-based Node-RED to visually encode alerting logic. So the principal scheme would look this way. We read events from Kafka topic. Then it goes to Node-RED. We pre-process it. We query Data Hub API or other APIs to gather information that is needed to prepare a transactional email, and we send it with transactional email service. So this is an event-driven solution. We had to make it easy to modify and to modify logic and message alert and message patterns. And we wished that it can be managed by data governance managers. So it had to be low code. And for that purpose, we selected a Node-RED, which is open source, low code, flow-based programming tool, which initially was designed for IoT applications. And building and knowing how to build and building very straightforward alerting logic in UI decreased time to market for alerting features. And we're going towards the end. We covered data and analytics governance with multiple metrics. I will not list all of them, but there are a few which seems to be very helpful. And here they are. It's a percent of products owned by domain owners, which we mentioned before, percent of data products covered by data quality tests, normalized rates of data quality test failures, percentage of data products covered with Lineage, and percent of assets covered by descriptions. Of course, there is always a possibility to dig deep and to distinguish good descriptions from bad descriptions. Very shallow and simple data quality test with comparing to a good data quality test. But in general, even simplistic metrics like this help data domain managers, data governance managers deal with the domain. So here are a few main takeaways. Scale makes brute force solutions in data and analytics governance not feasible. So if you have 100 or 1,000 tables, you can go one by one and assign owners. If you have 100,000 of them or 500,000, you can't. So in order to deal with this size of infrastructure, you have to leverage implicit knowledge. For example, Lineage, database usage patterns, and even redefine existing responsibilities. We do all of this to stimulate peer-to-peer communications between data owners and data consumers and make them direct. So these communications are crucial to success of any data and analytics governance initiatives. Hence, we treat computational data governance as a product, and we measure it and measure communication and alerting impacts on adherence to data and analytics governance principles. Thank you. If you have questions, feel free to ask them. I will be happy to answer. Goodbye.